Hello, my name is Manuel Rodriguez, and we are the group number one of Business Intelligence class. And this is our presentation for assignment number 3. Okay, so let's begin. Let's begin. We're going to start answering the questions of the assignment. So first, we have to predict the total debt in the country that we are assigned. The total debts caused by COVID-19. We're the group number 1, so we have Canada. Okay, so let's begin. The source data comes. I took this information from here, from this GitHub. This one is the GitHub I took. Here we can see a CSV file that has the time series COVID-19 deaths globally. Basically, has all the deaths that has happened in the pandemic in all the countries around the world. Here we can see this is the CSV file. The CSV file has the province, state, the country, the latitude, the longitude of the location, and it starts and it has all the days. Each day is a column. Every day is a column, and here we can see that here are the dates that start to appear. Basically these are all the dates that happen every day since January when the pandemic started and in all the countries around the world. Okay, so this is the CSV file. This is the data that we're going to work with. Okay, so I'm going to show you, because the first thing that we have to do obviously is to clean the data and to arrange the data to use what we need. Okay, so I'm going to show you. This is my Jupyter notebook, and here we have all the code that we use. Okay, so we're going to start answering the question number 1. Predict the total debts in Canada. Okay, so first, obviously, you have to import all the libraries that we need. We're going to read the CSV file that I just showed you with the total debts around the world. That's head. We can see the structure of the data that I already showed you. This is the same. So first, okay, I'm going to start cleaning the data. Okay, so I'm going to drop the latitude and longitude columns. I don't need that. I don't want that. And then I'm going to, this code is to arrange the data, because I don't want to have every single date as a column. I just want to have one column for all the dates and one column for all the dates that happen in that day. So this is what this code is for, and here we can see the final structure. We have the province, the country, the date in just one column. So we have all the dates starting on January. That's when the pandemic started, and the number of deaths that happen every day on every province, on every country. Now I'm going to filter the data, because I only need Canada information, so I'm going to filter that to Canada. And here we can see now we only have Canada information. And finally, I'm going to group that information by the date to sum all the dates, and I'm going to sort that so they're going to be in the right order. So here we can see my final data frame with all the information that I needed, that basically are the date and only the date and the total debts. I already filtered this, so I know this is the information only from Canada. Okay, so here we have our final data until now. Right now, that the last day we have is November 8th. Right now is November 10th, so it's up to date. We until now have 10,575 deaths in Canada because of COVID-19. Okay, so here we can see the information of our final data that we're going to use. We only have 2 columns, date and dates. Okay, so to answer this question, we decided to use the linear regression algorithm. Okay, so why did we choose to use this algorithm? Well, I think that this is the best one according to the information that we have. Well, first, because if, as we can see, the information has a tendency, because obviously they are just summing deaths day after day after day. So the tendency is that obviously this is going to increase. It has an increasing tendency. So I think that's our one reason because to use the linear regression, and also because, well, the linear regression allows us to make forecasts or to make predictions of some data. We have almost 8 months of historical data, so we have enough information to use the linear regression to make some good prediction based on that. Okay, so that's why we chose linear regression. Let's see how it works now. So first we have to assign the x and y variables of the linear regression. So for the x variable, this is basically a series. I just wanted to put the numbers from 1 to 292. Why? Because we have 292 rows, so we have 292 days of information. So right now, well, basically the x variable is just going to be the numbers from 1 to 9. It's a consecutive series from 1 to 900, from 1 to 292. And my y variable, that is my dependent variable, it's going to be the number of deaths. Okay, so now we import the library that we need to use to start working. And here we can see we're going to first separate our data into our training data and our test data. So we're going to have 30% of the data is going to be our test size. Okay, so here we have that, and well, basically this is what we sorted the data, so they appear in the right order, the x and the y from the test data. Okay, so here we have the linear regression. We use the linear regression function. We feed the training data into our linear regression, so we can get our equation, our linear regression equation formula. So here we have the intercept. This is the intercept of the formula, and here we have the coefficient of the formula, or the slope. So now that we have our formula, we can make the predictions. And well, this is our score of the data using the test data, or our R-squared. So we have that it adjusts, the linear regression adjusts to the information, to the data, in an 85%, in an 86, almost an 86%. And I think that's not bad at all to do the linear regression. Our R-squared, 86%. Okay, now we generate our predictions. Okay, until now, we already used the linear regression algorithm to generate our prediction. And now let's see how accurate the predictions are. So for that, well, I already said that it's almost an 86% of adjustment using the R-squared. And here we can see some graphs that we did. We plotted the y sorted, that are the actual values, and the prediction values that we have. Well, here we can see that, well, at some points, well, the values are very similar. Maybe at some points there are not. Usually the prediction values are a little lower than the actual values, as we can see. But they are okay. They are accurate. And now let's see. These are the errors using comparing the actual values and the prediction values. For example, if we see at the absolute error, well, we can see the absolute error, it's around 1,300. As we know, well, the total deaths right now are 10,000. So maybe we can say that the error is a little bit more than 10%, based on that the total deaths are 10,000, and our total error on our absolute error it's 1,000. So we can say, yeah, it's basically the error. It's a little bit more than that 10,000 that, well, obviously it corresponds to the same that we were saying with the R squared value. And well, here finally we can see this is the linear regression generated by us. The red dots are the actual values that we have, and this is the linear regression that we just generated. Here we can see the graph. It's very clear, and we can say that, well, it's accurate enough. Okay, thank you very much. And now, well, Ginu can continue with the other questions.
Hi, Professor Habibi. Thank you so much for your time. My name is Jingyo, and here I'm glad to give you the presentation for our group answer to the question 2 for assignment 3, which is predict the cumulative cases, the active cases, the incident rate, the case fatality ratio, and the testing rate in the country which are assigned to us. Because we are group 1, so our target country here is Canada. And this is the dataset I use, which is called the COVID-19 Canada.csv. And for most of the rows, for the most of columns of data, which is directly downloaded from the link given in the assignment page. But at the same time, in order to give the information of the total test and the recovery data from the source. Here, I also use data which is from the website of the Canada government. In this CSV page, I can find more information which will be helpful in my analysis. And in order to answer this question, here I will use the model which is called the autoregressive integrated moving average, which can be briefly called as ARIMA. So this model is actually used to fit it to the time series data. And the purpose is to have a better understanding of data and make the prediction for the future point based on the series. And this is the Wikipedia page for this model, and also there are a lot of the mathematical description and the formulation for the model, but it's not the point of our current presentation. Here, this is the code I use in order to execute and build a model, and eventually to make the predictions. Firstly, I just used Python functions to read our dataset COVID-19 Canada.csv, and we just import this to the dataset which is called DF. And then, in order to answer the first part of the question 2, which is the cumulative cases, here I just try to extract the column which is the total cases in the dataset. Yeah, total cases, this one. So, and also I try to plot the autocorrelation of this time series data, and here is the result. And in this chart, we can see that actually this data is very suitable for making autoregression model, because there is a very clear linear correlation at least for the first 200. Yeah, for the first 200 examples. So we will continue our process of the model building. And here, this part is the key part of the model building. So this is S1, which is the total case number. This is the description of the time series data we will use here, and this is the size, size of the dataset. And in this part, I try to split the dataset into two parts: the training part and the test part. So the training part will be the 7% of the original dataset, and test part will the test part will be the remaining 30%. So for the test part, for the test training set, for a test dataset, I will record them line by line into this list, which is called the history. And also here I just set a prediction list, which is called P total cases. And for now it's just empty, but by using this by using the code, the content of this for loop, I will just add the value of prediction line by line into this list. And here you can see the key part of the model building by using the pandas package, which is called ARIMA. And this is the model building, and this is the model fit, and this is output. Yeah, and we have each output which will be labeled as yard. And actually this yard is one line. Each is one line of the predictions, and we will just load it into the previously empty list, which is called p total cases. And also here we have another list which is called OBS1. So in this list we will just load the test datasets into this list, and also in this for loop it will just we will just have a full list of the test dataset, and eventually our target is to print the prediction list and the expectation and the real value list, and see what's the effect of the comparison. And so here is the result of execution, and you can see that this is the prediction value and this is the real value. And here is the plot of the prediction and the real value. The prediction value is in red and the real value is in blue. So we can see that actually the model is very good in trying to simulate the real situation. So this is for this part is for total case, and because the data I use here for total case is actually the accumulated cases. So by giving this list of prediction and this chart, I have answered the first part of the question 2. And so here we use the similar way and methods to get a prediction for another 3 columns of data, which are the total deaths, the total tested, and the total recover. And you can see that all these 3 charts, this one, and this one, has shown that the new model is very useful is very efficient in predicting the real value. So, yeah. And after having the prediction of all these 4 columns, which is the total case, the total deaths, the total tested, and the total recover, now we will be able to answer the remaining part of question 2, which are the active cases, the incident rate, the case fatality ratio, and the test rate. So here, let's go. Yeah, firstly, the active cases is actually the total cases minus by the total recovery. So by transferring all these prediction lists into the array, now we were able to calculate the number of calculate and get a list of the prediction of the active cases. And here is the plot of the prediction for the active cases for 87. Yeah, I think it's 87 lines or periods in the future. And this is the prediction of the incident rate, which is actually the total cases number divided by the total population of Canada. So this is plot, and we can see that the percentage of the confirmative cases has been increased for the prediction period. And this is the prediction of the case fatality ratio, which is actually the prediction of total deaths divided by the prediction of the total cases. So here we can see that there is a very clear trend of decrease of the case fatality ratio during this prediction period. And eventually here we have the prediction of the testing rate, which is actually the prediction of total tests divided by the total population of the country. So, and here we can see that the testing rate has increased from about 13% to about 26% of total population, which is increasing by time. Yeah, so I think this is the answer to the question 2. And thank you so much for your time. Yeah, and have a good day.